Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 1793, titled Maximum Score of a Good Subarray. This problem challenges us to find the maximum score of a subarray that satisfies specific conditions. Let's dive in and explore the problem, step by step. In this problem, we are given an integer array called nums and an integer k, where k represents an index in the array. The goal is to calculate the maximum score of a good subarray. Now, a subarray is simply a contiguous portion of the array, and its score is determined by two factors: the minimum value in the subarray and the length of the subarray. Specifically, the score is calculated as the minimum value in the subarray multiplied by its length. A good subarray is any subarray that contains the index k. What we need to do is determine the maximum score that can be achieved by any such good subarray. The input format specifies that nums is an array of integers with a length between 1 and 100,000, and each element lies between 1 and 20,000. The index k is guaranteed to be valid within the bounds of the array. The output will be a single integer representing the maximum score of a good subarray. Let's look at an example to understand this better. Consider the array nums equals 1, 4, 3, 7, 4, 5, and k equals 3. Here, we are tasked with finding the maximum score of a good subarray that must include the element at index 3, which is 7. One possible good subarray is 4, 3, 7, 4, spanning from index 1 to 4. The minimum value in this subarray is 3, and its length is 4. When we compute the score, we get 3 * 4 equals 12. This turns out to be the maximum score for this example. The key is to test all possible subarrays containing index k and find the one that maximizes the score. Another example illustrates this further. Consider the array nums equals 5, 5, 5, 5, and k equals 2. Here, every element in the array is the same, so the minimum value of any subarray will always be 5. The largest possible good subarray is the entire array 5, 5, 5, 5, which includes index k equals 2. The length of this subarray is 4, so the score is 5 * 4 equals 20. In this case, because all the elements are the same, the largest subarray results in the maximum score. This demonstrates that sometimes the entire array might be the optimal choice when k is included. Let's look at one more example. For the array nums equals 2, 4, 4, 4, 2, with k equals 2, we need to consider subarrays that include index 2. One such subarray is 4, 4, 4, 2, which spans from index 1 to 4. The minimum value here is 2, and the length is 4. The score is therefore 2 * 4 equals 8. However, this is not the maximum score. A subarray like 4, 4, 4, which spans from index 1 to 3, has a minimum value of 4 and a length of 3, resulting in a score of 4 * 3 equals 12. By properly evaluating all valid subarrays, we find that the maximum score for this example is 16. To wrap up, let's consider some edge cases. For the smallest possible input size, such as nums equals 5 and k equals 0, the only subarray is the entire array itself, 5. The score in this case is simply 5 * 1 equals 5. Another interesting case is when all elements in the array are the same, like nums equals 7, 7, 7, 7, with k equals 2. Here, the maximum score is obtained by taking the entire array, as all subarrays will have the same minimum value of 7. Finally, for very large input sizes, such as when nums.length equals 100,000 and all elements are a constant value, the score is determined by the length of the largest subarray containing index k. These edge cases ensure our solution is robust and performs well across all scenarios. To solve this problem, we first consider the brute force approach. In this method, we iterate over all possible subarrays of the input array nums that include the index k. For each subarray, we calculate the score as the minimum value within the subarray multiplied by the length of the subarray. While this approach is straightforward, it involves nested loops to calculate the minimum for each subarray, leading to a time complexity of n squared. This makes it highly inefficient for larger arrays. Additionally, since we're not using any extra space, the space complexity is 1. However, due to the quadratic time complexity, this approach becomes impractical for larger inputs. To address this, we can turn to a more efficient technique, the sliding window approach. Here, we start with the smallest possible subarray containing only the element at index k, then expand symmetrically outward while maintaining the minimum value in the subarray. This ensures that we calculate scores only for subarrays relevant to the problem. By using two pointers, left and right, to manage the boundaries, we can dynamically adjust the window to maximize the score while keeping computations efficient. Now, let's break down the sliding window algorithm step by step. We initialize the window boundaries with left and right both set to k, which means the subarray starts with just the element at index k. We also track the current minimum value in the window, which initially is nums, k, and the maximum score encountered so far, starting with 0. To expand the window, we move either the left or the right pointer outward, depending on which movement keeps the minimum value larger. At each step, we calculate the score as the product of the current minimum value and the length of the subarray, then update the maximum score if this new score is higher. This process continues until either the window covers the entire array or no further expansion is possible. By doing this, we ensure that every index is visited at most once, resulting in a linear time complexity of O(n). The space complexity remains O(1), because we're not using any additional data structures. This approach is not only efficient but also takes advantage of the problem constraints to avoid redundant calculations. In comparing the two approaches, the brute force method was ultimately ruled out due to its inefficiency for larger arrays. While it is conceptually simpler, its O(n)² complexity is impractical for real-world scenarios. On the other hand, the sliding window approach strikes a balance between time efficiency and simplicity. It avoids the need for additional data structures, making it both space-efficient and easier to debug. We also considered alternative methods, such as using segment trees to pre-compute minimum values across ranges. However, these methods introduce additional complexity without providing significant performance benefits over the sliding window approach in this specific problem. With its linear time complexity, minimal space requirements, and alignment with the problem's constraints, the sliding window approach emerges as the optimal strategy. It effectively takes advantage of the structure of the subarrays and the nature of the score function to deliver an elegant and highly efficient solution. In this problem, we are tasked with finding the maximum score of a subarray that includes a specific index k. The score of a subarray is defined as the product of the minimum value within the subarray and the length of the subarray. To begin, let's look at the brute force approach. First, we initialize a variable max_score to 0, which will store the highest score we encounter as we evaluate subarrays. The input consists of an array nums and the index k, which must be included in every valid subarray. Next, we iterate over all possible starting indices L for the subarray, ensuring that L is always less than or equal to k, since we must include k. Similarly, for every L, we iterate over all possible ending indices R, ensuring that R is greater than or equal to k. This guarantees that all candidate subarrays containing k are considered. Once we have identified a valid subarray with boundaries L and R, the next step is to calculate its score. To do this, we extract the subarray nums, L, R, and determine its minimum value. This can be done using a loop or a helper function. The score is then computed as the product of this minimum value and the length of the subarray, which is R L plus 1. After calculating the score, we compare it with the current max_score. If the new score is higher, we update max_score to reflect this value. Once all possible subarrays have been evaluated, the algorithm outputs max_score as the result. It's also important to consider edge cases. For instance, if the array has only one element, the result is simply the score of that element. If all elements in the array are the same, the score will be highest for the largest subarray that includes k. Finally, if k is at the boundary of the array, only subarrays starting or ending at k are valid. From this, we can draw some key insights. First, every valid subarray must include index k, so we only consider subarray boundaries where L equals k equals R. This constraint ensures that we focus exclusively on subarrays that satisfy the problem requirements. Now, when using the brute force approach, the time complexity becomes a concern. Iterating over all possible starting indices L requires O(n) time, and for each L, iterating over all possible ending indices R requires another O(n). Additionally, for each pair L, R, calculating the minimum value in the subarray involves yet another O, N, operation. Combining these, the overall time complexity becomes O, N cubed, which is highly inefficient for large arrays. In terms of data structures, we rely on the input array nums to extract subarrays and compute scores. We also use a single variable, max_score, to keep track of the best score encountered. While this approach is computationally expensive, it systematically evaluates all possibilities and serves as a baseline for optimization. To improve the efficiency of the algorithm, we can explore several optimizations. One key optimization is to pre-compute the minimum values for all subarray ranges. By pre-processing the array, we can store the minimum values for every possible subarray in advance, which reduces the cost of minimum calculation to O(1) during the main algorithm. This pre-processing step can bring the overall complexity down to O(n squared). Another optimization involves using the sliding window technique. Instead of evaluating all subarrays exhaustively, we can adjust the subarray boundaries dynamically while maintaining the minimum value efficiently. This approach leverages the structure of the problem to reduce redundant calculations and further improve performance. By implementing these optimizations, we can transform the brute force solution into a more practical and scalable algorithm for larger input sizes. This solution efficiently computes the maximum score of a good subarray that includes the given index k. The approach starts with k as both the left and right boundaries of the subarray and iteratively expands outward. At each step, it chooses to expand either the left or the right boundary based on the value of the neighboring elements, ensuring that the smaller of the two possible expansions is prioritized. Initially, the boundaries left and right are both set to k, and min_val is initialized to nums, k. This represents the minimum value in the subarray, which directly affects the score calculation. Max_score is initialized to nums, k, as it represents the single element subarray containing only nums, k. The main logic resides in the while loop, which continues as long as expansion is possible on either side, left 0 or right n1. Inside the loop, the algorithm decides whether to expand left or right based on the values of the neighboring elements. If extending to the left results in a greater or equal minimum value than extending to the right, it moves the left boundary leftward, otherwise, it moves the right boundary rightward. This ensures that the subarray's minimum value remains as large as possible. After updating the boundaries, the algorithm calculates the score of the current subarray using the formula min_val*, right left plus 1. It then updates max_score to be the maximum of the current score and the previously recorded maximum. This approach ensures linear time complexity, O(n), as each boundary is moved at most once. The space complexity is O(1), since no additional data structures are used. This makes the implementation efficient and well-suited for the constraints of the problem. This is the Java implementation of LeetCode problem number 1793, maximum score of a good subarray. The logic mirrors the Python implementation, where we expand the subarray boundaries outward from index k while maintaining the minimum value within the subarray. Java-specific differences include explicit type declarations and the use of Java's math.min and math.max methods for calculations. The solution efficiently computes the maximum score by examining all valid subarrays containing the index k. We are given the array nums equals 1, 4, 3, 7, 4, 5, and k equals 3, meaning we start at the index 3, where the value is 7. Initially, both the left and right boundaries are set to the same index, k, which is 3. The minimum value in the subarray also starts as 7, and the maximum score is initialized to this value, 7. Now, we begin expanding the boundaries. First, we compare the numbers adjacent to the current boundaries, nums, left 1, equals 3 and nums, right plus 1, equals 4. Since 4 is greater than 3, we extend the right boundary to include index 4. This updates the subarray to 7, 4, and the minimum value within this subarray becomes 4. The current score is calculated as 4 multiplied by the subarray length, 2, resulting in 8. The maximum score is updated to the larger of the previous maximum score and the current score, which is now 8. Next, we expand again by comparing nums, left 1, equals 3 and nums, right plus 1, equals 5. Since 5 is greater than 3, we extend the right boundary to index 5. now the subarray becomes 7, 4, 5, and the minimum value remains 4. The current score is 4 times the subarray length of 3, equaling 12. The maximum score is updated to 12. After this, we shift our focus to expanding the left boundary. Moving the left boundary to index 2 includes nums, 2 equals 3, making the subarray 3, 7, 4, 5. The minimum value decreases to 3, and the current score becomes 3 multiplied by the subarray length, 4, which equals 12. The maximum score remains 12. Expanding the left boundary again to index 1 includes nums, 1 equals 4, forming the subarray 4, 3, 7, 4, 5. The minimum value stays at 3, and the current score is 3 times the subarray length, 5, resulting in 15. The maximum score is updated to 15. Finally, we expand the left boundary one more time to index 0, adding nums, 0 equals 1 to the subarray. This results in the entire array 1, 4, 3, 7, 4, 5. The minimum value decreases to 1, and the current score is calculated as 1 multiplied by the subarray length, 6, which equals 6. The maximum score remains 15, as 6 is smaller. Therefore, the final output for this example is 15. In the next example, nums equals 5, 5, 5, 5, and k equals 2. The left and right boundaries start at index 2, where the value is 5. The minimum value and maximum score are both initialized to 5. To begin, we expand the left boundary to index 1, forming the subarray 5, 5. The minimum value remains 5, and the current score is 5 multiplied by the subarray length, 2, resulting in 10. The maximum score is updated to 10. Expanding the left boundary again to index 0 includes nums, 0 equals 5, creating the subarray 5, 5, 5. The minimum value is still 5, and the current score is 5 multiplied by the subarray length, 3, equaling 15. The maximum score is updated to 15. Now, we expand the right boundary to index 3, forming the subarray 5, 5, 5, 5. The minimum value remains 5, and the current score is 5 times the subarray length, 4, resulting in 20. The maximum score is updated to 20. The final output for this example is 20. In the final example, nums equals 10, 1, 10, and k equals 1. Here, we start at index 1, where the value is 1. The left and right boundaries are both initially set to index 1, and the minimum value and maximum score are both 1. First, we expand the left boundary to index 0, adding nums, 0 equals 10 to the subarray. This creates the subarray 10, 1, where the minimum value remains 1. The current score is 1 multiplied by the subarray length, 2, which equals 2. The maximum score is updated to 2. Next, we expand the right boundary to index 2, including nums, 2 equals 10 in the subarray. This results in the subarray 10, 1, 10, where the minimum value is still 1. The current score is 1 multiplied by the subarray length, 3, equaling 3. The maximum score is updated to 3. Thus, the final output for this example is 3. To analyze the time complexity, we start by looking at the initialization step. Here, variables like n, left, right, min_val, and max_score are assigned values, and these operations are constant time, or O1. Moving to the main while loop, this loop continues as long as either left can be decrement or right can be increment. In the worst case, the loop may execute up to n times, as the boundaries expand outward to potentially cover the entire array. Inside the loop, each boundary update involves a constant number of comparisons and updates, which are O1. Similarly, updating min_val requires a single comparison, and calculating the current score involves basic arithmetic, both of which are O1. Lastly, updating max_score also requires a simple comparison and assignment, making it O1. All these steps ensure that each loop iteration performs constant work. Now, for the total time complexity, since the while loop executes at most n times, and each iteration involves only O1 work, the overall time complexity of this algorithm is O(n). Next, let's consider the space complexity. The algorithm only uses a fixed number of variables, such as n, left, right, min_val, max_score, and current_score. Each of these is a scalar, meaning they require constant space, or O1. Additionally, the input array nums is not modified, and the algorithm does not allocate any extra memory for it. This results in a space complexity of O1. Comparing this optimized solution to the brute force approach highlights the efficiency of the algorithm. A naive solution would involve generating all subarrays that include the index k, which requires O(n) squared work. For each of these subarrays, we would then calculate the minimum value, which takes O(n) operations per subarray. This leads to a total time complexity of O(n) cubed, which is computationally expensive. In contrast, the optimized solution avoids this inefficiency by dynamically expanding the boundaries outward from k and maintaining the minimum value as it goes. This eliminates the need to repeatedly compute the minimum for each subarray, reducing the complexity to O(n). Let's break down the best, average, and worst case scenarios of this algorithm. In the best case, where the array has only one element, the loop does not execute at all, and the operations are limited to initialization, making the complexity O1. In a typical scenario, which we consider the average case, the loop iterates over a portion of the array, leading to a time complexity of O(n). Finally, in the worst case, where the boundaries expand to traverse the entire array, such as when k is at the start or end of the array, the complexity remains O(n). In conclusion, this algorithm achieves a time complexity of O(n) and a space complexity of O1, a significant improvement over the brute force approach. This optimization is made possible through the use of dynamic boundary expansion and efficient tracking of the minimum value. When solving this problem, there are a few common mistakes to watch out for. First, relying on a brute force approach might seem straightforward, but it quickly becomes impractical for larger inputs. This is because the naive method has an O(n) cubed time complexity, which is not scalable. Always check the constraints to determine if a more efficient algorithm is necessary. Another frequent issue is recalculating the minimum element in a subarray repeatedly. This can lead to redundant computations and increased complexity. Instead, techniques like a monotonic stack or two-pointer approach can help you efficiently track the minimum. Additionally, it's crucial not to overlook edge cases. For example, when k is at the start or end of the array, or when all elements are the same, or even when the array contains only one element. These scenarios can easily break a solution if not handled properly. Lastly, misinterpreting the problem constraints is another pitfall. Some might assume the subarray must start or end at k, but the requirement is simply that k must be included. Carefully reading the problem statement can save you from unnecessary errors here. Another common source of error is off-by-one mistakes when calculating subarray boundaries or lengths. For instance, when determining the range between indices L and R, forgetting to include both ends can lead to logical errors. Always double-check calculations like R, L+1 to ensure accuracy. Now, let's discuss some key insights for interviews. If a problem involves subarray ranges and minimum values, you should immediately think about tools like monotonic stacks, sliding windows, or even binary search on results. These methods optimize how you handle range minimum queries. To further improve efficiency, pre-processing the array can help. For example, identifying the next smaller and previous smaller elements for each index allows you to quickly determine valid ranges. Recognizing patterns is also important. Many problems involving subarrays and constraints, such as this one, share strategies with sliding window or monotonic deque problems. Finally, during interviews, communication is key. Make sure you articulate your thought process clearly, especially when explaining why a particular approach fits the problem. For example, you might say, "I'm using a monotonic stack because it efficiently tracks the nearest smaller elements, which is critical for this solution." The concepts we've discussed so far are closely related to other problems on LeetCode. For instance, problem 907, sum of subarray minimums, focuses on efficiently summing up minimums for all subarrays and shares similar optimization techniques. Problem 84, largest rectangle in histogram, also relies on ideas like finding the nearest smaller elements, making monotonic stacks a key tool. Another related problem is LeetCode 239, sliding window maximum, which involves efficiently handling subarray maximums, often using a deque. Finally, problem 85, maximal rectangle, extends the histogram approach to a 2D matrix context, showing how these techniques can be adapted across dimensions. Now, let's look at alternative approaches for this problem. One powerful method is the monotonic stack. This approach helps find the nearest smaller elements to the left and right of each index, enabling efficient calculations of ranges where each element is the minimum. Its pre-processing complexity is O(n), making it significantly faster than brute force. However, the trade-off is that monotonic stacks can be more complex to implement, so practice is essential to master this technique. Another approach is binary search, which can be particularly effective if the array is sorted or has specific properties. For instance, you can use binary search to quickly find ranges that satisfy certain constraints. This method typically has a complexity of O(n) log n, but it does require additional pre-processing or specific conditions to work effectively. Finally, there's the two-pointer technique. This approach uses two pointers to maintain a valid range dynamically, adjusting them as necessary to meet the constraints. It often runs in O(n) time and is simpler to implement compared to a monotonic stack. However, it might not apply to every variation of the problem, so its usefulness depends on the exact requirements. Each of these methods has its strengths and trade-offs, and the best choice often depends on the problem constraints and your familiarity with the techniques. Understanding these alternatives and knowing when to apply them will make you a more versatile problem solver. Great job working through this problem. To summarize, we explored how to maximize the score of a good subarray by understanding subarray properties and evaluating different approaches. Remember to practice regularly to strengthen your algorithmic skills. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!